So I've got a theorem here that gives us an idea of what the kind of properties that we can expect from trees. Right? And what this is telling us, right, is saying if we have a graph and it has n vertices, then the graph is a tree if and only if it's connected and has n minus 1 edges. So we're seeing a relationship here between the number of vertices and the number of edges in this particular special type of graph. So remember, this is an if and only if. It's a biconditional. That's kind of a math shorthand for combining two theorems into one. Right, so first this is telling me that kind of the forward direction, the conditional version is true. That is, if G is a tree and it has n vertices, then it has to have n minus 1 edges. Right, so this is giving us a property of trees. If we know our graph is a tree, then this relationship has to exist between the vertices and edges. We also get the converse. That's kind of going the other way. If G is connected with n minus 1 edges, then it's a tree. Right, so this is giving us a tool that we can use to take just kind of some arbitrary graph and determine whether or not it is more specifically a tree. Okay, so let's look at some examples here of how we can use this. Can a tree have 8 vertices and 9 edges? Well, the number of edges has to be 1 less than the vertices, which means if this thing has 8 vertices, to be a tree, it has to have 7 edges, not 9. Right? So the answer here would be no. This tree does not exist. Similarly, let's say a graph is a tree with 12 vertices. How many edges must it have? Well, it's going to have 11. That's 12 minus 1. Okay, so let's see if we can prove this. So we're going to start with the conditional here. We're going to assume that we have a tree and that it has n vertices. And I want to show that that means it has n minus 1 edges. All right, so we're going to do this by induction. All right, so let my statement here be P of n is a tree with n vertices has n minus 1 edges. Now the base case, that's going to be a tree with 1 vertex. A tree with 1 vertex, according to the formula, has 0 edges. And yeah, that does have to be the case. The only way for a tree with 1 vertex to have an edge would be if the edge connected the vertex back to itself. That would be for it to be a loop. A loop is a really, really small circuit. And because our graph is a tree, circuits aren't allowed, which means it can't have any edges. Okay, so how about the inductive case? So let G be a tree with k plus 1 vertices. I need to show that this tree has k plus 1 minus 1, or just k, edges in it. Okay, so here's how I'm going to do that. Right? Since k plus 1 is greater than or equal to 2, the graph must have at least 1 vertex of degree 1. I'm going to call it V. So what I'm going to do next is I'm going to look at that vertex V, and because it has degree 1, and because the graph is connected, there has to be an edge connecting that V back to the rest of the graph. I'm going to call it E. And remember, the vertex is degree 1, so that is the only edge connecting it to the graph. Okay, so let's say we take it away. Right? I'm going to define G prime to be identical to G, but with V and E removed. All right, that means that G prime has k vertices. It's connected. It has no circuits. Removing an edge can't create a circuit. Therefore, it must be a tree. And because its size is k, right, it's less than k plus 1, by the inductive hypothesis, it has to have k minus 1 vertices. And that's what I needed. Right? The only difference between G prime and G is that single vertex that we took away. Right? Which means G must have the k minus 1 vertices in G prime plus that 1 vertex V, which means it has k vertices, and that's what I wanted to show. So before I move into the converse side, we're going to need this little lemma here. It says if G is a connected graph and it has a circuit in it, and I remove a single edge from that circuit, that doesn't break the connectedness. right? The graph is still going to be connected without that one edge. Now, the proof of this, I've seen this done in some very, very precise, detailed ways where this starts by saying, well, let U and V be vertices, and then they create a path, V1, K1, V2, K2 through Vn, Kn, and then you take a vertex out, and then there's n minus ones. It's a lot more convoluted than I think it really needs to be for an idea that really is pretty straightforward. Okay, this is all based on the idea that if you have 2 points on a circuit, there are 2 ways to get from one of those points to the other, called the clockwise way and the counterclockwise way. Whichever one you take the edge out of, go the other way. Right? So here, let's see if we can be a little more precise about that. Right? Let E be an edge of the circuit, and I'm going to take it out. Right? So G prime is identical to G, but with that edge removed. So their vertex sets are the same, and their edge sets are identical except for E. Okay, so let U and V be vertices in the original graph G, and let W be a walk from one of them to the other. Then we have 2 cases here. First, that edge that I took out isn't in that walk. Okay, well then we're fine. Right? Then there is a walk from one of those vertices to the other one. Graph still seems to be connected. The other case, E is in the walk. All right, so that means we have a situation like this, right? We have this graph, and you can see the circuit there in the middle. You see how I took that edge E out of the graph. Okay, so we start our walk from U, and we go up and down and over, and then we run into trouble. Right? We hit this dead end because of that edge that was removed. Okay, well, go back to where you entered the circuit and just go around the other way. Right? And there you go. Takes you all the way to V. That's what you needed. That's what I needed to show. Right? I picked 2 arbitrary vertices and showed that regardless of whether that edge E is there or not, I can still get from one to the other, which means the graph is still connected. Okay, so now we're ready to go the other way. Right? If I have a graph, it has n vertices, n minus 1 edges, and it's connected, that's enough to force it to be a tree. Okay, so I'm going to do this by contradiction. So let's assume that we have a graph G. It's connected, it has n vertices, n minus 1 edges, and it's not a tree. Right? In other words, it has at least one circuit in it. So here's what I'm going to do. I'm going to build a new graph. I'm going to find that circuit, and I'm going to break it. I'm going to remove an edge. Right? And I'm going to call the new graph that I get from doing that G1. Now, maybe we're done, maybe we're not. I don't know how many circuits this thing has. Maybe it has more than one. So I'm going to keep on doing this until all of the circuits are broken. I'm going to call that new graph G sub K. Okay, G sub A is connected. That's why I needed the previous lemma. All I did was break circuits, right? It has no circuits because I built it that way. That means it has to be a tree with n vertices, right? Because I didn't take away vertices, just edges. The vertex set is still the same. Okay, well, since G sub K has n vertices and is a tree, the theorem we proved back at the beginning says it must have n minus 1 edges. But since we removed at least one edge from G to get to G sub K, that means that G must have at least n minus 1 plus 1 edges, but that's n. And that contradicts my assumption that G has n minus 1 edges. Right, since we've reached a contradiction, my original assumption must be false, so this graph will in fact be a tree. So we're going to see more of this kind of theorem that gives us relationships between the number of vertices and the number of edges in different kinds of trees. It can get a little overwhelming sometimes, try to remember them all, so it's helpful to have little tools to do that. The way I remember this one is with this example here. The super basic tree, yeah, And I can see immediately from this what the relationship is, right? I have two vertices and one edge. I see them and think, oh, right, n and n minus 1, there's my relationship. Okay, so in the next lecture, we're going to look at another special type of tree, right? Something called a binary tree. That, again, this is one of those things that shows up all the time in computer science applications.